Right, welcome to CCIE, the very first topic. Let's begin with routing information protocol. This is not new to us. We have seen this from the beginner level CCNA, but we are going to once for all see this completely and make sure we know everything. Routing protocols are to discover routes for us. That's why they are called as dynamic routing protocol. Dynamic routing protocol. So why RIP? Why do we need RIP? In order to dynamically discover the routes. Okay. If RIP discovers the route dynamically, what the other protocols are doing, like OSPF, EIGRP, BGP, can you say that? What other protocols are doing? If RIP discovers the route, if RIP helps to learn the route, what about the other protocols? Are they not learning routes?
Yes, they are.
They do. Then why do we need these many protocols? RIP, OSPF, EIGRP. Why? Why do we need these many?
RIP is a distant vector protocol, and it's not versatile as EIGRP or OSPF. It's not that versatile.
Okay. So RIP is a distance vector. That's a good point. Distance vector protocol. It's a distance vector protocol, but it is not versatile. That's what you said. Now, it's a bad protocol, no? Then
Yes.
why are we keeping bad protocol? Why do we need to learn this? If it is bad and you got something better.
Maybe some old equipment in the field still using RIP.
That's a good one. Okay, so you are saying like this RIP protocol is an older protocol. People started using it long back and still they continue using it. They have not migrated to EIGRP or OSPF, so we need to learn. That's a good one, but unfortunately, it's a good guess. It's not a right one. It's not a right answer. Why? Even in today's deployment, people enable RIP. Even in today's deployment, a new network when they design, they plan to have RIP. Why? What do you think about that?
I'm not quite sure why they would want to use it. Maybe.
Yeah. You see, this is not a bad protocol. This is also one of the best protocols. So people like to use RIP because they like RIP's approach in discovering route. Every routing protocol has got its own approach. As you said, RIP is a distance vector protocol. Distance vector protocol approach may be the one which you are expecting in your network. Distance vector protocol, how they work? They advertise the network information along with the hop count and with the direction. So for every network, you will know how many hops away the network is and on which direction it is. So in case if you need hop count as a metric for each destination, then this is the only protocol. This is the only protocol that can provide you the route information based on hop count. There are some companies who wants the route based on hop count. The route decisions
Okay.
need to be done based on hop count. They don't like the other way. They want to check which route has got less number of hops, and they want to their protocol. They want their protocol to pick that path as the best path. So RIP is the only protocol which can provide you route as per the hop counts difference. So when you got multiple paths, here you see I got one router, let's say R1 and R8. We got any other routers, router 2, router 3, router 4, router 5, router 6, router 7. So from router 1 to router 8, I got two paths. RIP is going to say this is the best because of the less number of hops. Just 3 hops, 1, 2, 3 hops. You can reach any network behind R8. But if I go the other way, it's going to be 1, 2, 3, 4, 5, 5 hops. So lesser the number of hops, better is the route. That's the metric of RIP. Less the hop count, better is the route. Yeah. Less the number of hops, less the hop count, better is the route. So don't underestimate this protocol. Very important. That too, when we say we are CCIE, we cannot say any protocol bad.
Right.
Especially RIP is an important protocol. Wherever you need hop count as a metric. Now, give an example where hop count is very important, not any other metric. Try to think and give me an answer. Take your time. What will be
Where
the
hop
best
count.
use case of RIP? I say hop count should be the metric. They don't want any other metric. Now, what is the use case? Where is that hop count is important, not any other metric? Can you guess? Can you?
Yeah, I'm thinking.
Good.
I'm thinking. I'm not quite sure. I'm not quite sure if I can come up
No
with an answer.
problem. I'll help you. You see, you have this router here connecting to the internet cloud, let's say, or it may not be internet cloud. It can be your own office, but a big network. That's why I'm drawing a cloud there, a big network, and you got another router here, R1 and R2. Now I have a tunnel established between these two, a tunnel, a GRE tunnel, let's say. You know GRE tunnel?
Right.
Now, if you will run OSPF and RIP, and when you learn routes to reach from this A network to B network, you need to learn routes. You need to learn route to reach B the routing table here. You should learn route B. Only then you will be able to ping B, isn't it?
Right.
Now, you have connected a virtual link called tunnel, and you want the traffic to go through the tunnel. Tell me, which one will have less bandwidth? Is the physical link or the tunnel link? Which one will have less bandwidth? Less bandwidth.
The tunnel will have less bandwidth.
Very correct. Yes. So will OSPF use the tunnel?
No.
Because the bandwidth is less, isn't it?
Right.
OSPF
Yes.
calculates the cost using bandwidth. More the bandwidth,
That's correct.
less the cost. So
Yes.
if you use OSPF, traffic will not take the tunnel. It will try to use the physical path. But when you use RIP, it will see just one hop because it's tunnel. And all the traffic to B will go via tunnel. You got the use case? You understood?
Yes. Yes. Yes.
So, RIP is not a bad protocol. Very useful protocol wherever tunneling comes into picture. Because we want the hop count as a metric. We don't want the
Right.
traffic to go via the physical path. We want the tunnel to be used. So when I use RIP, it won't use the physical path, because if you go via the physical path, then you will see a lot of hops. But when you go through the tunnel, it is only one hop. Yeah. RIP is also a instant protocol. Next. About RIP, we already saw hop count is a metric. And you already gave me a very nice answer. It's a distance vector protocol. It shows the distance. It shows the hop count. And also it shows the direction. In this example here, what is the direction? Tunnel. Tunnel path is the direction, not the physical path. You need to go via the tunnel. In this picture, what is the direction? Router 2 is the direction. Via this direction, 3 hops. Yeah. So via this direction, it will have 5 hops, so lower is better. That's why it's distance vector protocol. Distance vector protocol. Now, this protocol has got some limitations. We see as a limitation, but it is right to say rightly. We no need more than 15 hops actually. You see, I use RIP in this type of scenario where the tunnels can be used. Do I need more than one hop here to reach B? Not necessary.
No.
I don't need more than one hop. If my router can support one hop, that is enough. So RIP says I can support up to 16 hop, max hop. 0 to 15 hops. This is seen as a limitation. According to me, it's not a limitation. This is reasonable. I no need too many hops because I'm using RIP in where? The tunnel topology. Wherever I got tunnels, that is where I use RIP. It's a distance vector protocol. So for the topology where I use RIP, there is no really need for more than 1 or 2 hops.
Right.
So 15 hop max is reasonable. Next. This protocol don't discover any neighbor. No neighbor discovery. No neighbor discovery. They don't discover neighbor. If you take any other routing protocol, all other routing protocols will discover neighbor. Can you give me an example for a protocol that discovers neighbor and the timer,
Yes.
along with the timer?
I think OSPF
Okay,
and the timer. Not quite sure. 20 seconds. I'm not quite sure.
no problem. OSPF every 10 seconds send a
20
hello.
seconds. Okay.
That hello packet helps to discover neighbor. OSPF sends hello packet every 10 seconds. And that hello packet helps to discover neighbor. So neighbor discovery is not there in RIP, which means no hello packets. RIP never send a hello packet. Then how do you know RIP routers are alive or dead? You see, in OSPF, every router sends a hello packet every 10 seconds. That gives a confirmation that the neighbor exists.
Right.
But in RIP, no hello packets are sent. Then how do router 1 knows that router 2 still exists? How router 1 knows router 2 exists? It's still alive. How it knows?
Isn't it? Does it use some multicast address there?
It's a nice point. See, instead of sending hello packet, RIP sends the entire routing table as an periodic update. It sends updates every 30 seconds
30.
periodically, whether there is a change in the routing table or not. Even when there is no change in the routing table, it will send the updates. It will send the entire routing table every 30 seconds. Periodic update every 30 seconds. Yes, it is good that it sends periodic update. If no periodic update is sent, then a router will not know about other router whether it is alive or dead. For example, I got router 1, router 2, just two router. And here I got 1.1.1.1. Here I got 2.2.2.2. Now let's say router 2 has advertised 2.2.2.2, one hop. Router 1 has advertised 1.1.1.1, one hop. Now, after advertising, if they don't speak, if they don't send any hello packets or periodic message, then if 2 goes down, how router 1 will know that this 2.2.2.2 is no more? Router 2 has gone down. Router 2 has gone down, but already router 1 has learned about this network. If router 2 goes down, how will router 1 knows that this network don't exist anymore? So there should be something, this is something that makes other router know that this network has gone down. So when there is no periodic update for 180 seconds, 180 seconds, when there is no periodic update for 180 seconds, that that destination, that network is considered dead. You see, when router 2 goes down, this update will not come anymore. It's supposed to come every 30 seconds.
Right.
Now it's no more coming because the router has gone down. Now how long router 1 will be holding the root in the routing table? It will be holding 180 seconds. After 180 seconds, it will inform everyone that I have waited 180 seconds and it is no more, so let us flush it out. What is the flush interval? Do you remember?
I'm not sure.
Okay.
No, I don't remember.
240 seconds. 240 seconds. So, what is 240 seconds? 4 minutes. Yeah? 4
Right.
minutes. This is 3 minutes. After waiting 3 minutes, it concludes that the network is down. But it won't remove it. It removes the 4th minute. So in between this 3 and 4, what happens is, router 1 informs everyone that earlier I was having root, but now it's no more available. The root is poisoned. The root is no more available. It informs everyone that root is no more available. We call it as route poisoning. I'll come to the topic a bit later, but now what I want to say is, we don't have hello packets. Instead, we have periodic update. What is periodic update? Every 30 seconds, the complete routing table is shared so that others will be updated. If others are not getting update for 180 seconds, then those other routers will consider this router as dead. And to remove the root from the routing table, it takes 240 seconds. So far good?
Yes, sir. Yes, sir.
All right. So
Hop count is used to determine the path of data flow. It is better to use the rip because it uses the hop count, so maybe 1 or 2 over some other routing protocol.
Wonderful. So they don't focus on the bandwidth nor the delay. They do focus only on the hop count. So a lot of tunneling technologies only focuses on hop count. There is where we use RIP. Okay, next is how RIP confirms that the root still exists.
Well, for every 30 seconds, it sends the entire routing table to the its neighbor, if you want to say it like that. So every 30 seconds, it will send the entire update to the next router.
Okay. Every 30 second updates are sent. We call it as periodic update. That makes the receiving router to confirm that the route still exists. So it is sent to which address? It depends on the version. If it is version 1, which is default in Cisco, but not with every vendor, you see. In most of the vendors, version 1 is not default, version 2 is default. What is the difference between version 1 and version 2? Version 1 uses the 255, 255, 255, 255, which is a broadcast address to send the update. So updates are not sent to the neighbor. Updates are not sent to the neighbor because they don't discover neighbor. They don't know who the neighbor is. All the time, every 30 seconds, they send the update to this address. If you send to this address, because it's a broadcast address, everyone is going to receive the update. Everyone in the network is going to receive the update. What about a printer? If I have a printer or a scanner or some computers, do they also receive the RIP update? Yes,
Yes.
because you are sending to this broadcast address. RIP version 1 uses broadcast address in order to send the periodic update, whereas RIP version 2 sends the packet to 224.0.0.9. This is what makes RIP version 2 much better than version 1. How? You see, if you want to send a traffic to a multicast, what's the advantage of sending? When I send to
It
a...
doesn't send. Okay.
Yeah, go ahead.
No, but it doesn't send to everyone. It's sent to only those routers that are in that multicast group.
Yeah, that is right. But you see, when you are sending this 224.0.0.9 traffic, truth is, everyone is going to receive it, even the printer, even the scanner, but they don't process it. The wires will carry the update, no doubt. In both the scenario, the update goes to everyone, but when the destination address says to all, then everyone thinks, because it is said all, this may be something useful for me, so let me open it and let me try to process it. When they process it, it's a meaningless message for printer, scanner. So they unnecessarily process it and drop it because they don't understand what is RIP. But they have processed it, they have wasted their process. Whereas, when you send to this address, the printer receives the packet and printer says, I don't know who is 224.0.0.9, it's not me. I'm not going to accept this packet. It won't be even accepted. You understand? So, when you send to a multicast address, when you send a traffic to a multicast address, only the member of that multicast group will be able to receive it. That is how you need to explain. We should not say it is not sent to printers. We should say it is sent to a multicast address, but only those RIP running routers will be able to accept it. Because in order to receive a packet that is sent to 224.0.0.9, in order to receive the packet that is sent to 224.0.0.9, one must be running RIP. Otherwise, they cannot join that multicast group. Yeah. So, sending to a multicast address reduces unnecessary process utilization on the receiving device. If the receiving device don't run RIP, they will not receive this packet. Okay. So big difference between version 1 and version 2. Version 2 uses multicast, version 1 uses broadcast. Next. The other big difference is this version 1 can accept the packet of version 2. Version 1 running routers will be able to receive the updates, will process, will accept the update coming from version 2. Version 1 can receive version 2 update. it can receive, because it is version 1. It says all. I'm ready to accept any one. It can receive version 2 update. Whereas version 2 router, version 2 running router will not receive version 1's update. Because version 2 is very precise, Version 2 says, I'll receive only the packet that is given to this address. But version 1 is giving update to which address? Version 1 gives update to which address?
Version 1 give updates to all.
Broadcast, correct. It's called broadcast.
Right.
When you send a packet to a broadcast address, version 2 says, hey, no, sorry, I cannot accept. I'm very precise. Only if any packet, if I see a packet coming to 224.0.0.9, I can receive it. Otherwise, no, I cannot. So version 2 don't receive if packet is sent to a broadcast. So in short, what I want to say is version 2 is not compatible with version 1, whereas version 1 is compatible with version 2. You got this point?
Yes, sir.
Okay, version 1 is compatible with version 2 as well as version 1, whereas version 2 is compatible only with version 2, not with version 1.
Right.
Now, there is something called split horizon rule. What is split horizon rule? What is the connection between this rule and the protocol RIP? You see, split horizon is a rule that says the route that is received on an interface should not be advertised back on the same interface. That's simple it is. If you will learn some network like 1.1.1.1 on F01, if you are learning that in F01, then this router should not, router 1, if it learns that 1.1.1.1 in F01, router 1 should not advertise 1.1.1.1 back on the same interface. It can advertise it on the other interfaces like Ethernet 0, Serial 0, F02, no problem. They can advertise it over the other links, but not on the same link. This is what split horizon is. The route learned on an interface will not be advertised back via the same interface. Now, this is very important for distance vector protocol. Let's say this router 2 is advertising this 11111. Now, router 1 receives it from router 2, and when it is sending the update will not go back to router 2. That avoids loop.
Right.
How it avoids loop? Say, for example, after advertising 1.1.1.1, router 1 will say 1.1.1.1 is one hop away from me. Now, after advertising this, router 2 has lost connection to this. Network. That network no more exists. It's gone. Now, if split horizon rule is not there, what will happen? The periodic update that will come from here will say, for me 1 hop, for you 2 hop. So router 2 will learn that 1.1.1.1 is 2 hop, which is a wrong information. And now if someone is trying to ping 1111, the packet comes to router 1 will send it to router 2, and router 2 will send it to router 1. Again, router 1, because router 1 learned it from router 2. Router 2 learned the route from router 1. This is going to cause loop.
Okay.
To prevent loop, we got this split horizon. And that split horizon is even before you enable RIP. The split horizon is running even before you enable RIP. So don't think that this is something RIP's feature. No, this feature is there all the time, even before RIP. For RIP, this is an advantage. For RIP protocol, this is an advantage. To prevent loop, split horizon is used in RIP. So, what is the loop prevention mechanism in RIP? If someone asks, what is the loop avoidance mechanism in protocol RIP, you should say split horizon rule. Now, if they will ask you a question like, what if the split horizon rule is disabled? What if the split horizon rule is disabled? What will be our answer? Our answer is the hop count. The max hop is 16, right? So in case if there is a loop, it won't go more than 16.
Okay.
Yep. So what is the loop prevention mechanism in RIP? Split horizon. If split horizon is disabled, the max hop 16, infinite metric 16, will avoid loop. So the loop will be for just 15 cycles. After that, it will disappear. Loop will be prevented. So every protocol has got loop prevention mechanism. For RIP, it is split horizon rule. But split horizon is not enabled on after you enable RIP. It is enabled already, even before you enable RIP. For RIP, it has become an added advantage to prevent loop. And in case if there is no split horizon, if someone for some reason disabled split horizon, the
hop count,
max hop count, infinite metric 16, helps to prevent loop. Now, in RIP, the last topic is the route poisoning and poison rivers. What is route poisoning and poison rivers? Route poisoning. Let's say we got router 1 connected to router 2 connected to router 3. And this router 3 has got a network to advertise, let's say 3.3.3.3. Now, when router 3 advertises this network, what will it say? It says 3.3.3.3 is one hop away for you. Am I right? Now, router 2 in its routing table, it learns that 3.3.3.3 is one hop away. And router 3 will advertise saying 3.3.3.3 is 2 hop away for you. So according to router 1, what is the number of hop? What is the distance?
2.
3.3.3.3 is 2 hop away. Now, what if after giving this advertisement, this network goes down? Tell me, what will happen? After advertising to every other router, the network has gone down. What will happen? Router 3 will stop advertising this because it is gone now. Okay. Now this guy will start waiting for an update. Usually it gets update every 30 seconds. But now R2 will not receive any update. So it will wait for 180 seconds. It will wait for 180 seconds. After waiting, it will turn this hop count as what? Possibly down.
Okay.
You will see in the routing table PD, not PD. It will very clearly say possibly down. The complete word.
Right.
Now, as soon as it makes the route to be possibly down, instead of sending 2 hop away, it will send 16 hop away now,
Okay.
which makes the router 1 to consider this as possibly down. So router 1 need not to wait for another 180 second. No, router 1 need not to wait. As soon as it receives 16, router 2 has already waited and it has confirmed that it is possibly down. So it is flooding this information by putting 16 so that all will switch to possibly down. If a route
Right.
is possibly down, it will stay only for another 60 seconds. So totally how many seconds now it took for flushing it out?
Total to just 60 to 40
Yeah,
seconds?
180 plus 60, 240 seconds. Yeah, in 240 seconds, the entire topology will throw the route out because of route poisoning. What is route poisoning? Sending this 16 hop instead of 2 hop. We call this route poisoning. We want to poison the route. We want to say that route don't exist. Don't use it. So by putting 16, it poisons everyone. So everyone will throw this route away in another 60 seconds. Okay, that is route poisoning.
Right.
Then what is poison reverse? Poison reverse. Poison reverse is here. You see, usually split horizon will not allow update to go, right? Split horizon will not allow 3333 update to go back to router 3.
No.
But when the route is considered as possibly down, after waiting 180 seconds, router 2 will go back and reconfirm by sending 16 hop. It will go to router 3 and say, hey, router 3, 3333, 16 hop. What do you say? It wants to confirm. And router 3 will be silent. If router 3 is silent, which means the route really don't exist. This is what called as poison reverse because it goes in reverse direction. It is allowed to override the split horizon only after considering the network as possibly down. We call it as poison reverse. Can you explain me the difference between route poisoning and poison reverse?
Right. Road poisoning is whenever a route is being disconnected from a distant end router, then it's the closest router to the distant end router send the hop count of 16 to all other router, so they can have it in their routing table as possibly down.
Yep.
After 60 minutes, the entire network will be flushed from that,
No,
flush
it's not
that route out
16
of
minutes.
the
Sorry
network.
to interrupt you. It's not 60 minutes, it's 16 seconds. 60 seconds.
60 seconds, sorry, 60 seconds. I mean 60 seconds, I'm
No
sorry.
problem, no problem.
60 seconds,
Yep.
the entire network will flush that route out of the network. Poison reverse is used to override split horizon from the closest router that received the route from the distant end router, so that
It can reconfirm.
no, it's just to verify,
Yes.
just to verify if the router is really down
Yep.
or not, because it might down for a while and come back up. If the router is silent, then it know that it's done for real.
Exactly.
Then it go ahead and flush out the system.
Wonderful. All right. So now what is left in RIP is RIP authentication and a few more optional things like changing the timers in RIP, you know. So those things we'll do in the lab. Yeah, we will do in the lab. Today
Okay.